Presentation is part of the course assignments playlist, and in this case it relates to the final coursework. Keep in mind that this final coursework is a grading assignment that corresponds to 25% of your final grade in this course. Since it addresses the boundary scan test domain, you should start by revisiting the boundary scan test presentations, which took place in the very beginning of our course and which are still available in the corresponding playlist in the lesson pages of our course website. After watching this presentation, you shall be able to explain what are the objectives and the functional specifications of the system proposed for this final coursework, and you should be able to set up a plan to begin your work. Now, the envisaged deliverable comprises the three main blocks that you see in this slide, and the three of them will be implemented into the FPGA that is present in the Nexus 3 board. Now, this system will be based in the PicoBlaze embedded core, which will run an interpreter to execute a set of test program commands and data that are stored in the local FPGA memory. The code and data will be received via RS-232 from the PC using a UART receiver, which is implemented into the FPGA as well. Now, the PicoBlaze embedded core will be responsible for controlling the test access port of the board under test. So it will generate the bit stream to be shifted into the test data input pin, and it will generate the appropriate signals for the test mode select and test clock inputs of the test access port. Now, at the same time, and whenever required, it will read the bit stream coming from the test data output and compare this bit stream with its expected results. Now, the minimum functional features comprise at least one test access port. Our system should also accept a set of serial vector format-like commands. Serial vector format is a test representation format that was developed jointly by Texas Instruments and Teradyne, and you can read more about that at this Wikipedia page. Actually, what is being asked in this coursework is a simplified version of SVF. So our system shall be able to receive the test code serially using an RS-232 port, and it should support one push button for running the test and two LEDs to indicate the test result, either pass or fail. The minimum set of SVF-like commands to be supported by our system is represented in this table. So it comprises a reset command, which, as the name indicates, simply takes the boundary scan logic to the test logic reset state. It supports also TMS 0 and TMS commands, which shall be used to go from one state to another in the test access port controller state transition diagram. It supports one simple shift command, which simply scans a given bit stream, in this case X, into the selected scan chain, be it instruction or data registers. It supports a shift and compare command, which is a more sophisticated version of the previous command. In this case, and besides shifting a given bit stream X into the board under test, this command will read what comes out, that is, and compare it with an expected bit stream given as Y, using another bit stream given as zeta, which is used as a mask. That is to say, for each bit shifted into the board under test, we will read the bit that comes out and compare it with an expected result that is given in bitstream Y. Now, because not all of the bit positions will have known or expected value, we need a mask information, and that is the reason why the set bit stream is needed. Finally, the multiple TCK enables us to generate n test clock cycles while keeping TMS at 0. End of program is not really a command, it simply marks the end of the object code. We will convert the source code into object code using a universal table-driven cross-assembler. In this case, I recommend you to use the Telemark cross-assembler, or TASM. This is a shareware program that is available freely in the internet, and it uses a table to convert any set of source commands into the corresponding object code. In this case, what this slide shows is one possible table to convert the given source commands into one possible set of corresponding object codes. Now, the allocation that was used in this table was arbitrary, and you can of course choose a different allocation. Please read the information about the TASM cross-assembler to understand the meaning of the remaining fields in this table. Now, the test workflow comprises 4 steps, so we will start by writing the test program using the source code in SVF-like format. This source code will be compiled into object code using TASM, which generates a file containing the object code in Intel X format. That is to say, the object code is actually a text file that comprises the object code in this format. Now, this text file will be sent using the RS-232 connection to the Picoblaze memory. And the test program will be run by pressing the corresponding button in the Nexus 3 boards. Now, the expected deliverables from this coursework comprise code, be it VHDL or assembly, or even C if you prefer to write your interpreter in C, but I do recommend that you use assembly instead, or otherwise you will not learn so much about the architecture of the Picoblaze embedded core. It also comprises the test benches that you will use to validate your work, so that will be the VHDL test benches as well as any SVF programs that you may use with the demonstration board when you validate your prototype. And finally, you are expected to produce a set of slides presenting your work. Now you may ask yourselves, how do I start? There are possible ways to do it. One of those possible ways is shown in this slide. So you may start by just implementing the 3 blocks shown in the previous slide, that is to say the UART receiver, the memory module and the Picoblaze embedded core into the FPGA, and run a very simple experiment. That is to say, you may, for example, use the LEDs in the Nexus 3 board to show the ASCII code that you have just received via RS-232. Then at the same time, someone else in the group may start by drawing the state diagrams for each of the test commands and to write its implementation code in Picoblaze assembly. Now, if you look at the reset command, for example, what you will have to do is to set TMS at 1 and then generate 5 clock pulses at TCK. So for each of these test commands, you can actually draw a state diagram that specifies the set of elementary operations that have to be carried out in order to execute each command. And then, of course, you should integrate and validate one test command at each time. So if you have implemented reset, please check that it is operating by watching at the corresponding waveforms, and then only you should move on to the next command. Now, to conclude, I leave you a number of possibilities that you may consider if you wish to take this work further.